After we have discussed the theory of the random forest classifier and implemented a model in Python, I also want to briefly discuss the random forest for regression problems. This is only going to be a short video, so I will not go into details like I did for classification problems. For classification problems, the random forest algorithms use several decision trees that make a class prediction. The ideal thresholds for the splits within the trees are identified with the help of Gini impurity, entropy, or log loss. The way random forest works for regression problems is not so different. It also uses decision trees, but uses different formulas to find the best thresholds for the splits. Those can be the squared or absolute error, Friedman mean squared error, or Poisson. So let us see how we can solve a regression problem using population data. I already added some imports that we have also used in the last lecture. Additionally, we will need the random forest regressor itself. So, from sklearn.ensemble, import random forest regressor. And we need a suitable error metric. So, from sklearn.metric, import mean absolute error. Now let us look into the dataset, which comes from the Worldometers website. We set up a variable that will hold the dataset, then use pd.readcsv, and open the data which lies in the subfolder data and is called population.csv. Now let me print the last observations within the dataset, which we can get with df.tail. You can already see that the data is not cleaned up this time, as NaN values are present. To see if those are the only NaN values, I check for them with df.isNull.sum. In this case, we only have this one none data point, which comes from inaccurate data preparation. So we use df.dropNA and make it an in-place operation, so that NaN observations are removed from this data frame. Then I check for NaNs once again, and this time the dataset is clean. What I also want to do is to divide the population counts by 1 billion to improve readability. So I get the world population column from the data frame, and then say that its content should be divided by 1 billion. Now this looks better to me. We can also plot the population against the years to see the general trend of the data. I use sns.scatterplot for that. The input data is our data frame. The y data should be the world population. And the x data, the year. Now we say plt.show and see that the world population increases each year. The next step is to sort the data into x and y data. For x, we will simply drop the world population column from the dataset. So df.drop, provide the column name within square brackets, and set the axis to 1. Then I only want to receive the data frame's values and thus turn it into a NumPy array. Next, the y data, for which I only select the world population from the data frame and also extract the values. Then we proceed with a train test split, for which I will again copy the expression from the documentation to make sure we do not mix up the variables. Then we provide x, y, a test size of only 20%, as we do not have that many observations. A random state of 42 again if you want to receive the same observations as I do for training and testing. And then we set the shuffle to true, as the data is currently sorted by the years. Next, we can already set up our regression model behind a variable that I will call model, and get an instance of the Random Forest Regressor. I will leave all the settings on their default values except the random state, which I will again set to 42. If you do that as well, your model will deliver the same results as mine, but you do not have to do that. After executing the cell, we can again see all the settings. The model used the squared error as a criterion and deployed 100 estimators. Just as the last time, we predict our test data next with model.predict. We get back a predicted population for each input observation. Like for 2020, when there was a density of 53 people per square kilometer, the model predicts 7.9 billion people. To check how far those predictions are off the real population count, we can calculate the mean absolute error. Based on the real wide test data and our predictions. In my case, the mean error is 0.05, which means 50 million people away from the real population. Now I want to show you one last thing. I will set up 2 lines of code that can do a prediction for some custom data points that we generate. The variable input will hold an NP array, into which we will write a first data point. I will take the year 1990 and a population density of 36, which is a real observation in our dataset. Now I need to reshape this array so it fits into the model. I say .reshape, provide a -1 first, which is kind of a wildcard, so NumPy figures the dimension out by itself. In this case, it will add a dimension to the data point, which is needed for the model. And then a 2 at the second position, which stands for our 2 features in the array. Then I say model.predict and put in our input. I leave away a variable in front of that, as I do not intend to reuse the result and just want the result to be printed. So the model predicts 5.3 billion people, and indeed there lived 5.327 billion people in 1990. And now I want to predict the future population for 2050 and assume that there will be a population density of 60. The model predicts 8.05 billion people for that. And that is already kind of strange, as we have 8.1 billion people in 2024. Let me try out something more extreme with the year 2100 and a density of 100 people per square kilometer. And the model still predicts the same population count of 8.05 billion people. You might already see that the Random Forest Regressor has a weakness when extrapolating data. The Random Forest Regressor uses decision trees just like the Random Forest Classifier does. In this illustration, only the years are considered as an input feature to keep it simple. The last split says that if the year is 2023, the model should predict 8.09. And if the year is higher than that, it should predict 8.16. Now, it does not matter how far we go into the future, it will always predict 8.16. Sure, this figure is simplified a lot, but it should just illustrate the underlying problem. Due to that, the Random Forest Regressor struggles to extrapolate data. So sometimes a simple linear regression might already do the job.